Okay, thank you very much. Hi, everyone. My name is Xiaofeng Liao. Here, I would like to introduce our work on a fair data model for the PRISMA study. Let me briefly give some background information of the PRISMA. PRISMA stands for Personalized Risk-Based Memo Screening. In the Netherlands, women aged 50 to 75 years are invited to receive breast cancer screening every 2 years. So the study aims to optimize the effectiveness and efficiency of breast cancer screening through personalized screening regimens based on women's risk, of breast cancer. I would like to give you some numbers regarding the data. So within the PRISMA study, we collect data on breast cancer risk factors. So as mentioned, that population is a population-based cohort of women of 50 to 75 years, and we collected 70,000 unprocessed mammograms, and also there are 43,000 health questionnaires are completed by the participant. And we also collected 10,500 blood samples. All these data are supposed to link to Dutch Cancer Registry. For this talk, we are mainly working on the 43,000 health questionnaires. So this is the data we are working on. During our work, we find a critical problem. That is, there is no universally accepted data model for the collection of breast cancer risk factors. This lack of interoperability would impede the clear data representation and communication globally. And the collected data has potential for validation work and machine learning, but this is obviously hindered by the lack of interoperability. So with this problem identified, we have some objectives on this work. The first one is that we would like to reduce ambiguity of data schemas in the domain and increase secondary use of client-reported outcome through verification. The second objective, a more specific one, is that we create a fair semantic data model out of the PRISMA questionnaires. So with this objective, get to the data, the questionnaires. We mentioned that we worked on the questionnaires. We have 43,000 questionnaires, and each questionnaires contains 211 questions. On the right, you see a word cloud that illustrates some of the topics covered in the questionnaires. So you can easily see the various topics, for example, type of work, family history of cancer, and infant pregnancy, alcohol use, and physical activity, etc. So it's, you can feel that it covers various topics. And next, I would like to introduce the processing of questionnaires. So here you can see it is an iterative process. It starts from a question. So for example, the first question, have you ever been diagnosed with a form of cancer? So for this question, we identified an ID, or we call it a variable. In this case, is diagnosed with cancer. And for this ID or variable, we identify a code system. In this case, we use the NCIT. And in NCIT, we try to find an existing match for this ID or variable. So, after this question, we continue to working on following the second one, the third one, and goes on. So here you see the second question. we again identify an ID variable and the code system, and then the next we identify the code for this ID or variable. So this loop goes on for all the questions in all the questionnaires. So I would like to say this is a huge amount of work, considering the number of the questions and the number of the questionnaires. Uh, so this is generally how we process the questions. In this slide, I would like to also look at the process we deal with the answers. You see that it's almost similar to what we did to the questions in the previous slide. Again, we start from answers. And the answers, for example, if there are some options, for example, if a question is about the type of cancer, then there are already defined answer options. For example, here we provide a list of cancer types. And for each type of these cancers, we also identify a code system. And then for each type of the cancer, we find existing match for these answers. So this is the processing of the answer. Also, it's an iterative procedure. Also, it goes through all questions and all questionnaires. Also, it requires a lot of human work here. So with the questions and answers are processed, we would like to give you a statistic number here. As mentioned, we try to identify a code system and find in the code system a match for these variables. So in this graph, you see that we have identified 188 variables out of the 211 questions and answers. And for this, we identified 188 variables. And you see that the most frequently code system that we can find existing matching is the NCIT. But unfortunately, it only covers only 100, around 120. And after that, you see there's a sharp drop on the number of the matches that we can find in the existing system. So this also indicates the critical problem we identified in the earlier of this slide, that there is no universally accepted data schema. So that also indicates our objective, that we would like to create a data schema out of our questionnaire. So I would like to show you this graph. We call it common data elements that we identified. So previously we mentioned that we have 188 variables. And from out of these 188 variables, we identified 67 data elements. And all these 60 data elements you can see on the screen, that in each of them in a rectangle. And all these 67 data elements were grouped into 15 main classes. All these 15 main classes are put on the first row. And for each main classes, it is organized in is a relationship. Here we can see some example. For example, here, family history of cancer. Has a subclass, family history of breast cancer, and it could also have family history of cervical cancer. And the third one, family history of ovarian cancer, is also a subclass of the family history of cancer. Another example is that we can look at the treatment. The first subclass of the treatment would be a non-surgical procedure, and under it there is a subclass chemotherapy, and another subclass for the treatment would be surgical procedure. And if we go on, we can see some other terms. For example, breast enlargement could be a subclass of the surgical procedure. So with this common data element identified and the hierarchy built, we would like to continue using the semantic science integrated ontology to build a model that connecting the question and the answers together. So what is semantic science integrated ontology? It is an ontology that is capable of modeling. Here I use different colors to mark the main objectives. Well, the first one is entities, process, and their qualities, attributes. You can also see this several key components in this graph. The first one is object, or maybe entity, and the second is process, and the quality and the measurement. These several key components are connected by the established property. Here you can see in the graph. So this is SIO ontology. And why we use its ontology? The reason is that most of the concepts derived from the questionnaires are measurement of some of the attributes of the women who participate in the study. So we can find connection between the SIO and our questionnaires, the data in our questionnaires. We link them with these color lines. So and women can be treated as an entity, and the measurement can be treated as a process, and the attributes can be treated as quantities and attributes. So in this way, the data element identified in the PRISMA study can be instantiated according to the core element in SIO and connected using the established property. So I'd like to show you an example. So I think I should not do, if you viewed the slides previously, you see some of the work from the HAPRD that they also using the SIO ontology. And yeah, we also using the idea to take the idea to using the SIO to model our questionnaire. That we connect the question and answers in one single framework. So this example here, you see we can have entity. It can be a participant, and it can be has a role and can be client, and this role can be have identifier, and then it goes through or is realized in the process. This process can be, in our case, in a questionnaire, could be have a type of detail and has a value. This value is our question. So in our case, for example, have you ever had a surgical procedure for breast cancer? Then this process could get an output. This output is an answer from the participant. It's maybe about some measurement, and this measurement could has some value, maybe a yes or no answer, and this answer could refers to an attribute. In this case, if it is a yes or no answer, then it is a Boolean type. So you see that we can using the SIO ontology to connect the questions and answers connect together in one single framework. So here we come to the conclusion. We identified 7 common data elements from the questionnaire and grouped it into 15 main classes. And the questions on this and answers were modeled by utilizing the core elements of SIO ontology. So in this way, we build a fair data schema for common risk factors for breast cancer. We can look at these 4 principles. The first one, findability. We published our data schema on external repository on GitHub. Regarding accessibility, we use using a license, we choose a license for it. And interoperability, as you can see in the slide, that we build up the linked data representation for all the data elements. And regarding the reusability, this work, we think it could be a potential template for other breast cancer research groups and maybe for real-world experience questionnaires. Some thoughts about the future direction. We maybe would like to model the questions hierarchy, because in the questionnaires, the questions could have some relationship or a hierarchy between them, or maybe a follow-up questions, this kind of this relation. And we would like to invite use cases like the PRISMA semantic data schema can support. And we would like also consider the interoperability with other standards, for example, EHR. At last, we would like to acknowledge our collaborators from different affiliations and also from the different projects, for example, CrossGenomics, PRISMA, and HAPRD. And also, we would like to thank the sponsors behind this project. So that's the slide for today, and I thank you very much for your time, and I would like to take questions.
Thanks so much. Do we have any questions from the audience? Tiffany has some questions that she posted in the chat. I'll ask those. And if anyone has any other questions, you can think about them. First of all, how did you select the terminologies that you used to map the answers?
Sorry, how do I select
the terminologies that you used to map your answers?
So yeah, we worked on the question, and as we see the process, we go through the questions, and there are 211 questions in each questionnaire. So we examine each question, and for each question, we locate ID variable, and for each ID variable, we try to map them to existing code system, or we can call it an ontology. So that's how we deal with this. We build these data elements. Hope that answers your question.
Yeah, and she further asked if you considered aligning to any of the OBO Foundry ontologies, like the human phenotype ontology or the Mondo disease ontology.
As we showed in the slide, we find that mainly on the, so let me show you this slide. So these are the code system or ontology. We mainly find the matches for our ID variables. The most used one is NCIT. Regarding the several ones you mentioned, unfortunately, we didn't find on the bio portal much of the maps for our ID or variables.
Okay, and last question is, could you describe the process that you use to validate your alignment between the answer fields and the terminologies you selected? Validation or?
Sorry, can you repeat that? It's not quite clear.
Yeah, was there a process for validating the alignment between the answer fields and the terminologies you used?
Sorry. Can I see the question? I didn't see the chat. Sorry.
Yeah.
Validate your alignment between. Okay. So validate the alignment between the code system. I hope that I get your answer correctly. So there are several criteria when we select in the code system, and we try to build the mapping. For example, we would like to choose the ontology that is actively maintained and maybe actively developed, and considering its citation, number of citation. So it's history. So several criteria we are consider when selecting the code system. All this work are manual work, we examine a bio-ontology portal. So that's generally how we validate the mapping